that. But now we can move on to our speaker, Dr. David Roueche. He's an assistant professor of civil engineering at Auburn University, where he researches of improving the performance of low-rise buildings under extreme load conditions, including hazards and tornadoes. Dr. Roueche performed extensive field research in the aftermath of some of the strongest events, including the 2011 tornadoes in Tuscaloosa, Alabama, and Joplin, Missouri, and again 2015 for the Garland, Texas event. Also for major hurricanes, 2017 Hurricane Harvey, Irma, and Maria. Dr. Roueche is got his doctoral degree, his PhD in structural engineering from the University of Florida, also his master's, and his bachelor's in civil engineering, also from the University of Florida. He was awarded an NSF Graduate Research Fellowship in 2013, which is very noteworthy. Dr. Roueche, thank you for coming to speak to us again. I know we had a bit of a hard time last time, but great. Yeah. I will stop sharing this and let me know if you are able to share your presentation with us. Here we go.
I think I can as soon as you stop. So there we go. Can you see that?
We can.
Oh, good. Awesome. Well, thank you, Richard, for the introduction. And it was great to meet you and some of the other GSC members in person just a couple of days ago at the NHERI Summit. And so hopefully many of you others were able to go to that. It's fantastic, fantastic meeting. And it's good to see your leadership and all there. So what I'm going to sort of talk to today is just I'm not going to go into super great detail in any one of these, but try to weave a little bit of a thread through several of the projects that are either ongoing or I've recently finished, sort of looking at where we're at in tornado resilience. And of course, as Richard mentioned, low-rise buildings is near and dear to my heart. And so it's going to maybe be a little bit more shifted towards that. But I think there's some broad applications beyond that as well. So lots of pictures and some videos, and but a little bit of fundamentals in there as well. So hopefully this will be useful and interesting. So I want to start with, I can get it, there it goes. I want to start though with just, if you've been paying attention to the news at all, this has been a fairly active year for tornadoes, especially in the Midwest this year. And so we've been seeing perhaps scenes like this come across our news feed and in different areas. So this was from Barnesdale, Oklahoma, back in May 7th, and I believe one fatality in this area, not specifically in this area, thankfully, that I'm showing here, but you can see just the level of destruction and imagine what the community used to look like and what were people's homes and lives and investments and so on that are now completely demolished from this extreme event, these tornadoes. And again, I showed just this one. There are lots of them that we could pull from recently, and I believe it was even last night or maybe the night before, tornado of some sort hit Houston. There seems to be a lot of damage there as well. So there's impacts we're constantly seeing, and it seems this year it may feel like it's been more than usual. But if you look at sort of a history of where we are, this is kind of a daily count and running annual trend of tornadoes from NOAA. And you can see the average trend line there in sort of the dark gray, and then where we're tracking right now in the red. And we're a little bit above average, but not, it's certainly not anything close to, record-setting pace or anything. I think a big part of it is just we've seen these sort of big outbreaks, and then let me jump to my laser. So you've seen sort of these big outbreaks, here and here and here, which coincidentally is something that even as far back as maybe 6-7 years ago, several researchers started pointing to sort of climate models showing that there may be sort of the impact of climate change on tornadoes being that there may be more clustered outbreaks, and perhaps this is a sign of that actually coming to fruition. But certainly it's been an active year to sort of remind us of the devastation that these storms cause. And even going back in a more holistic view of this, again, using data from NOAA, this is looking at billion-dollar disasters, kind of year to date. Event costs, so sort of a cumulative, and look at it. And this does, of course, does not include this year, but it goes from 2023 and back. And what you'll notice is that, of course, in terms of losses, a lot of the highest losses have been in recent years. We've got 2023, 2020, 2017, 2021, et cetera. And I believe if I grab the correct chart here, these are actually just convective storms. So things like tornadoes and hailstorms and thunderstorms. So this is not a new problem by any stretch of the imagination, but it also is, the impacts are increasing and are certainly still present, increasing depending on which metric we're looking at. So this is sort of a focus so far on kind of damage, and we've seen that it's definitely increasing, potentially climate change affecting that, but also just the growth in exposure. There's more targets in the area because of the urbanization and sort of the sprawl, urban sprawl and things like that. But when we look at fatalities, this is one where we see, okay, with tornadoes, are we at least doing better with fatalities in terms of warnings and so on? And so if we plot tornado fatalities by year from 1950 until last year, we can see that we've certainly made some improvements overall. And sort of the red line here is a 10-year running average. And we sort of made some improvements, but it's sort of stabilized here. And depending again on how you look at it, this is just absolute fatalities, but population, of course, has increased significantly over this time. So if you're looking at, say, tornado fatalities per million people or something like that, there's a little bit more of an obvious downward trend. But we're still getting a significant number of tornado fatalities every year, and approximately 75% of all tornado fatalities occur in homes, which is one of the things I'm going to focus on here. So stepping back then, if we're wanting to reduce, let's say tornado fatalities, there's a few different ways that we can do it, but it's a very interdisciplinary process. And so, on the right-hand side in green, we're sort of looking at one path to reducing fatalities is, well, let's get everyone out of vulnerable homes into shelters. So these all comes into advanced warning systems and communication of those, of the risk, and building shelters and getting people access to those shelters and transportation and all of the factors that go into sheltering behavior, and ultimately whether the home is occupied or not at the time of the tornado. But then there's the other path here on the left-hand side that's more of the traditional engineering approach, which is, well, even if people can't get out of their home, if they are having to shelter in the home, we can also reduce the risk of fatality by improving the structural resistance. So if we have stronger homes, then as the tornado impacts it, we're less likely to be in these really high damage states that are linked to high fatality risk. And so there's sort of two paths then to reducing tornado fatalities, and then of course all the indirect impacts that happen from that. One being more on the, again, keeping the vulnerable home from being occupied, getting people into shelters, and then the second is actually hardening the homes themselves. And of course, this is not an exhaustive look at it, but it's sort of an illustrative look at the various disciplines and all involved in this. So one that sort of related to this, sort of which path then should we go down? Just share a couple of highlights from a really interesting project that I'm so glad I had to be a chance to be a part of with collaborators from the University of Illinois. Some of you may know Frank Lombardo. Worked with him, as well as Daphne Ledoux and Laura Mayo at the University of Oklahoma, two social scientists. And so here we're looking at what can we learn from tornado survivor stories. So after an event happens, we are going into the field and we developed and then deployed this inner science protocol where we're actually interviewing survivors at the same time as we're doing detailed forensic assessments. Dr. Lombardo's team was mapping the wind field using wind indicators, and then we're sort of trying to bring all of this together to get a more holistic understanding of how the tornadoes impact structures and impact lives, but then also sheltering behavior, how they're receiving warnings, and then even how can we sort of link up what we're seeing, hearing from the survivors versus what we're predicting or what our models are saying from the engineering side. And so this sort of just gives a summary of what type of data maybe we're collecting and the interviews and follow-up prompts and so on that we're doing there. And so from this study, we responded to 9 different tornadoes, mostly across the Southeast, which was our study region, primarily just due to the funding that it came from. And we're trying to collect this unified data set that sort of links structural engineering, fundamentals of that, type and strength of the connections and degree of damage from the EF scale and type of foundation, et cetera, with the meteorological and wind engineering features, along with the social science. And then, of course, some of these are discipline specific, and then others, as you can sort of see in these Venn diagrams, sort of overlap, and we're learning from each other. We're getting data that helps both. And then ultimately, I'm not sharing a whole lot of it here, but then we also then shared a lot of that knowledge back with the survivors as well, in terms of rebuilding and construction and strengthened homes and giving them perspectives on the damage that they experience. And so it was a very rewarding, mutually beneficial, we felt, study. And so, for example, just a way of sort of bringing all this together, this is kind of a case study of a home from one tornado where we're sort of looking at the damage that occurred and documenting it and the structural load path, et cetera. Dr. Lombardo's team was using the tree fall patterns and some other indicators to condition a parametric tornado wind field. And then from that, we can generate a wind speed and wind direction time history from that wind field. And then we can start to link it up with a survivor story where they're telling us where they sheltered at, which in this case was down in the basement in this kind of southeast corner. And they're describing to us, well, this window blew in first, and then this happened, and then the mattress gets sort of sucked in through this bedroom and around the corner and so on. And so now we're able to take that information and then say, well, how does it compare with what we're predicting in our parametric tornado wind field model? Are we seeing an agreement here? What can we still improve upon? And then where they sheltered, is that, were they able to get to their ideal shelter? Did it perform as we expected? Was there in hindcast, was there a better place to shelter? Did it line up with sort of the general criteria, the guidelines that are out there on sheltering? Interior of the house, lowest story, et cetera. Was that really the best case for them here? And so this is just a very sort of general overview of it, but it's been really a fascinating way of sort of bringing all this together and looking at sort of these different paths, looking at sheltering behavior. And one of the interesting things that sort of me as an engineer was seeing in the data was that, as people shelter, what actually motivates their sheltering behavior. And what we started to see was that the belief we sort of characterize it as a belief in threat. So as a tornado is approaching, how strong is their belief that threat to them personally is actual? And then once it reaches a certain point, it motivates action. And what we were seeing was that belief in threat is highly influenced by the presence of multiple coincidence threat indicators. So it may be some environmental cues, it may be the TV broadcast, it may be a phone call from a friend, and alerts on their phone, just different things that are all sort of working together to sort of increase their belief in that threat. And then until at some point they're like, all right, we're past the threshold, which of course is going to be dependent upon how risk averse they are, and then they seek shelter. And so there's a lot of fascinating things that we can learn from this in terms of social science, of sharing risk and warning communication and so on. But sort of the takeaway from us as engineers is that as we're doing all these studies, all these interviews, is that the vast majority, 95% of the survivors all chose to shelter in their homes, even if they had time to sort of get elsewhere. And so that sort of goes back to sort of that original sort of network that I showed earlier, that relying upon mobilizing vulnerable occupants to safer shelters is just not a realistic pathway to a goal of zero fatalities, of reducing fatalities as much as possible. And so many people just choose to shelter in place for a variety of reasons, that hardening the home, giving safer options inside the home is something that should be a priority for us going forward. So if we're going to strengthen the home, though, improve harden that and get it to perform better, how do we do that? Well, unfortunately or fortunately, depending on the different perspectives, we've been looking at this going way back. So all the way, 50 years ago, the Lubbock tornado was really one of the first that sort of coalesced a community around kind of wind engineering and specifically wind hazard engineering and trying to strengthen buildings to resist tornadoes and other severe storms. And when you go into this original report, a fantastic report, if you're at all interested in tornadoes, I would encourage you to take a look at it. This is by Dr. Kishore Mehta. Many of you may know him, and then others, and Jim McDonald and some others, Joe Miner, that were involved in this, and really just a fundamental, foundational study. But if you look at some of their sort of summary recommendations or findings, most of the damage was caused by winds in the range of 75 to 125 miles an hour. The pattern, sort of the variance and performance, is better explained by the abilities of the structures to resist the wind forces rather than on these complex vortex wandering and picking up and dropping and things like that. The severe damage or total destruction can be traced to the failure of a structural component or a weak link in the structural system. Wood frame buildings, failures were initiated by inadequate connections. Okay, if you've been at all involved in sort of wind hazard mitigation, these are the same things we're saying now 50 years later. And so the sort of the question then I think that comes to mind is, if we've known about the solutions to mitigating tornado damage for 50 years now, is there really any more value in doing engineering research? Is this really just a social policy problem at this point? The engineering has already been solved. And so that's sort of the question. And you may even go further if you've been paying attention again to wind. And I know, I don't know how many here are sort of more wind focused versus earthquake or other hazards. But if you've been paying attention to wind, you may have seen that tornado design provisions are in our design standard for the first time in ASC 722. And this was a fantastic effort by Mark Levitan and others at NIST, sort of coming out of recommendations from the 2011 Joplin tornado. And it's a fantastic step forward. And so you may think, okay, yeah, we've solved it all. We've got design provisions. We know sort of the practical details of what to do. Is there anything left here? But when you start digging into it, we see that, for example, even in these tornado provisions, they really only apply to kind of category 3 and 4, which is our high occupancy or critical facilities. And then because tornadoes have such low probability of occurrence, even in ASC 722, the tornado design usually doesn't control over the straight line wind provision. So it's in there, but it really doesn't control unless you have really large footprint buildings at a high risk category. So we're not really addressing sort of the community resilience aspect of our neighborhoods and commercial buildings and sort of typical structures with this, which is okay. We've got to start somewhere. And I know this will continue to be advanced and improved as we go further. But I'll sort of just summarize here a couple of questions that will sort of form the basis for the rest of the talk here. And that is, there's still lots of questions that we need answered in order to really address tornado resilience. Up at the top, what's an optimum performance goal for tornadoes? Should it be life safety? That's all we care about, is just bringing those fatalities down to zero. Or should we also think about repairability in a tornado, or no damage at all? And what intensity levels for that? Are we wanting no damage at all in an EF5 or an EF1? Do we want life safety in an EF5 or an EF2? There's all sorts of questions that we as a society, we as engineers and so on, have to wrestle with and have the fundamental data to be able to inform those decisions. We talked about this a little bit. Should we invest in storm shelters or in safe rooms, or do we harden structures to address both repairability and survivability, but maybe not at absolute protection levels? What are the actual wind speeds and other near surface wind characteristics? Okay, right now they're estimated based on damage. We don't directly measure them for the most part. So we really don't know in most cases what the actual wind speeds are. We're trying to infer, knowledge about the damage when we're then estimating the wind speeds based on the damage. So we have this circular reasoning in a lot of our analysis that's hard to separate from. And we could go on for lots of other questions even beyond these. What resistance do we have in our non-engineered structures, if we're really going to improve them and say, not just, well, if you do this, it's going to be better performance, but how good? Well, we need to understand what the actual resistance of these structures is. And then ultimately, how can we educate the public, sort of use our engineering knowledge to then break down some of these longstanding misconceptions and actually advance policies as well. And so really the key, I love this quote. Some of you may have seen this before. I use this all the time. It's the statement says anyone can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. And the sort of the takeaway or the application here to tornadoes is that I could probably give any one of you the challenge of build a tornado-proof home, and you could go do it. Okay, if cost was not an issue and you were just designing something, sure, throw some concrete at it, throw some steel, harden it, put it underground. There's all sorts of ways that we could make a tornado-proof building. But now if we're starting to bring in costs, and if we're starting to bring in just the probability of a tornado strike, and what communities and homes have a finite resources, how are they best going to invest those and use those on a daily basis, thinking about long-term risk. We've got to be able to optimize structures to a point where we're optimal, having these optimal designs for a low probability, high impact event. You need very high levels of accuracy, high levels of precision, and understanding the science to sort of narrow in on, okay, this is what we need to do in this situation to achieve these performance levels. And unfortunately, in wind, and specifically with tornadoes, there's all sorts of uncertainties that we don't know. And so this chart here just sort of, again, qualitatively illustrates some of those uncertainties. But everything from either on the load side and the resistance side, it's fraught with uncertainties in the hazard itself, and sort of terrain effects and the aerodynamics of the buildings, to then design and construction, especially for these non-engineered structures, white wood frame structures that have very redundant, kind of complicated load paths. And then you start throwing in building code enforcement and quality and all these other factors into it. And there's huge uncertainty bounds around what we're trying to do that makes it problematic or difficult to really advance specific sort of performance-driven solutions to the tornado resilience problem. So again, quickly here, I'll just run through a couple of projects that sort of tie to this. So one is this one that PhD student Brandon Riddlemeyer has been working on, which is a probabilistic wind uplift resistance framework. And if you've done any maybe fragility modeling of wood frame structures, or familiar at least with that sort of area of research, you'll know that there's quite a few studies in this already that will kind of build arch types and assign connection capacities and apply loads from ASC 7 perhaps, or some other source, and then sort of run fragilities on these. But informed by our sort of damage surveys, our field work, we're finding that there's a lot of sort of nuances to the load path that are just not being captured by a lot of the existing studies. And in particular, we want to be able to look at, for a typical load path like this, focus primarily on the wind uplift resistance, which is how most of our structures fail. Is we want something that's computationally efficient, widely adaptable, where we can swap out different components very easily, and sort of look at this as a load chain and identify what's the weakest link, what's sort of a reliability perspective on all the links in that chain, and what is it currently for given structures that we encounter in the field, and then what's an optimal sort of load path, if you will, to really control the failures, and then to identify what the weakest links are. And so he kind of built out this framework of again, a Monte Carlo simulation framework, where we're defining the load path, sort of the links in the chain, where we're looking at where elements or connections of the connection are in parallel versus in series, and sort of summing all these up into idealizing it as one sort of probabilistic chain, and then running lots of simulations to figure out what is most likely to fail, where does failure initiate, and then as we sort of upgrade different pieces of that chain, what's the net benefit on the overall system. And so what's been kind of cool from that is that, we have this probabilistic output where we have the component level, uplift resistance distributions for the different connections within the load chain. We have the probability that it's the weakest link in that load chain. and then sort of the distribution of the system uplift resistance. And now we can sort of play with those parameters to see how it changes the overall distributions. And so we can play, affect things like the wood species, the mechanical properties of it, and then the connection size and spacing and, overlap of sheathing and just practical details that we see in the field all the time. Now we can encapsulate in a computationally efficient model like this. And so we may have a reference case, which we see all the time of, toenailed roof to wall connections and other sort of typical code compliant construction. And then if we swap it out, let's say we just throw a hurricane tie on there and say, okay, that's going to solve all our problems. Well, it fixes this one connection. So now in our original framework, the roof to wall connection was the most likely to fail. We've upgraded. And so that basically eliminated that one failure from occurring. But now we're much more likely to have basically what we call double top plate failure, which is sort of just immediately downstream from that, is now the most likely to fail. And then perhaps more concerning is we're more likely to have a foundation failure now because we upgraded the connection at the roof to wall. And so without addressing anything else, we may have improved the performance in some events, but we've actually made it worse in stronger events because we're more likely to have a foundation failure. But if we say use an H8 that ties kind of the rafter to wall and these double top plates, kind of eliminates both of those, and then say use the correct washers and anchor bolts, now we're getting in a more ideal failure reliability of this entire system, where we want it to fail at the roof sheathing. That's the safest failure, and then we're less likely to see these more severe failures occur. And then we've improved the overall resistance as well. We've sort of shifted this distribution to the right. So this is a cool education tool and other things that we can use to sort of optimize these non-engineered structures. And then we actually applied this to a recent tornado, the Araby, Louisiana tornado, and looking at how current construction is and how we can sort of shift some of these things and look at different combinations that we encountered in the field or even recommendations for rebuilding and see what's going to give us the most benefit, what's going to sort of shift our fragilities the most to the right with some small, again, very, very small adjustments, but meaningful ones to the overall structural resistance. So that's been kind of a cool aspect of that project. And then what about the wind speeds? So as I mentioned earlier, we really don't know what the wind speeds are in tornadoes. We indirectly estimate them based on damage. So one of my students, Daniel Yaya, who's a member of the GSC, is working on a project where we're trying to advance kind of our understanding of near surface wind characteristics in tornadoes from citizen science videos. So we'll get videos like this that get taken of tornadoes, and it's lots of debris flying around in it. And some of the debris is, moving vertically in all different directions. Can we take those videos and learn anything about the wind speeds or maybe the vertical component of the wind or other characteristics from the debris motion? And so this project involves both sort of this, what we call unstructured debris flight, as well as an extensive set of testing at the Florida International University Wall of Wind to get a structured debris data set as well that we've captured with lots of cameras. We know the background flow, et cetera, to be able to develop better methods of estimating wind speeds or inferring wind speeds from this debris motion. And so this gets quite complicated when you look at it, because yes, we may clearly see this debris trajectory, but it's got a large mass, so we can't just assume it's a tracer moving at the speed of the background flow. We've got to be able to incorporate the equations of motion into this. Well, in order to do that, we need to know the mass of the debris and the aerodynamics of that debris. We also need the sort of these 2D trajectories or 3D trajectories in real world coordinates. And so trying to back out all of those parameters, as you can imagine, there's a lot of uncertainty to it. So is there any value in doing this? Can we get any reasonable estimates out of that? And so a big part of this framework has been, again, work done at the FIU NHERI Wall of Wind. So there's Daniel loading up some chambers on a building. So the wind tunnel is sort of just upstream of this. And we built sort of all these chambers in here that we then loaded with common debris objects and some standardized, plates and rod-like debris and so on, even spheres that are very well behaved in terms of an aerodynamics aspect, as well as typical construction debris. And then we have a series of electromagnets that allow us to apply loads. Let's get this to play. We apply loads to the structure, in this case, brought the wind speeds up to 145 miles an hour. We release the electromagnets, panel flies off, all the debris then gets injected into the flow field, where we're capturing it with lots of cameras to then give us a structure data set where we know the mass of the debris and the shape and so on. And we're capturing it with videos from all different angles where we can triangulate the trajectory and then sort of downsample to our just sort of 2D cases and what type of wind speeds are we inferring, what computer vision techniques can we improve upon for identifying and tracking the debris as well, and ultimately get better estimates of the near surface wind characteristics in tornadoes. So that's been a really cool one as well. And then somewhat lastly here, I'll also mention one. If you know me at all, you know that field work is a huge component of my research, something I'm very passionate about. And I would encourage you all, if it's possible, to get involved with as well. And I'll say a little bit more about that in a second. But there's so much that we can learn from just going out into the field. And so this sort of transitions into some things that Jordan Nakayama is working on as one of my PhD students as well. This is her in the Arabi tornado, getting ready to put a drone up in the air to capture some of the damage here. And yeah, in learning, yes, we can develop all the models we want and sort of work through all that, and there's definitely value to that. But at some point, we've got to be able to validate those. We need high quality data, reconnaissance data, where we're capturing the right features, we're doing it in a consistent way that we can then use to validate these models and advance our understanding from a more data-driven perspective as well. And so that's where it's been fantastic being able to be involved in STEER. I'm one of the associate directors of STEER, the Structural Extreme Events Reconnaissance Network, which is then a part of Converge and the whole sort of NHERI infrastructure that the National Science Foundation has done such an amazing job at investing in. And STEER is open to anyone to join and be a part of. There's opportunity for virtual responses, in-person responses. So I would encourage you all, if you're not familiar with it already and you're interested in structures at all, or really anything related to even that would involve structural performance, sign up for it. At least you're aware then of what STEER is doing, and become involved in some of the virtual responses, and then even some of the in-person responses as well could be available to you. So as part of that, some of Jordan's work has been putting together, sort of pulling data sets both from STEER as well as some of my own that I've been involved with over the years from recent tornadoes and hurricanes, and trying to unify the data from all these events in a standardized way. And so right now we're up to around, and actually I think that number may be an older number, but I think we're over 6,000 structures now that we've documented. These are all, at this point, we're working the data set of just single family homes, where we've got the location and basic building attributes and an estimated hazard intensity, component level damage percentages, and then we're starting to add on some other features as well that we know are important as well, as we can standardize them. So now we've got them, all of this is a unified, what we call it's a multi-event windstorm performance data set, or the WISP test bed for single family residential structures. And what's interesting here, when we start looking at things across multiple events, comparing tornadoes and hurricanes, is that we see a significant difference between the damage patterns and the performance levels in hurricanes versus tornadoes. Here on the bottom here is sort of a high level where we're just saying what's the percentage of buildings in our data set that have roof structure damage or roof substrate, which is kind of your decking or sheathing damage, roof cover, et cetera. Fenestration is just your windows and doors and things like that. And in blue is tornado, and yellow is, or gold is the hurricane. And in all of these cases, we see a much greater percentage of buildings with damage, particularly sort of fenestration damage and then heavy structural damage in tornadoes than we do in hurricanes. And when we look at the empirical fragilities, which are what these are, so looking at on the x-axis our wind speed, and then our y-axis of the probability of being in these certain or exceeding these certain damage states, limit states, for, again, in this case, roof damage, so roof structure, roof sheathing, roof cover. And you can see a significant difference between tornadoes and hurricanes, where hurricanes, we really have some odd-looking empirical fragility functions. We believe in part because of the design constraints are so different. As you get closer to the coast, you have higher winds or higher design wind speeds and windborne debris regions and other things that actually, as you get to higher wind speeds, we're actually seeing less damage in some of those areas because the engineering design that goes into it seems to be playing a significant role. But then tornadoes, it's sort of where we're like, okay, well, what do we actually see here? Because we're seeing what seems to be a clear trend of increasing damage with increasing wind speeds. But then recall that we're estimating wind speeds based on the damage. So there's sort of a circular, and it's sort of smoothed out and in different ways. And we use tree fall models maybe, or sort of other ways of conditioning these parametric models. But it seems well behaved, but is that real, or is that, is there other things just in terms of how we're estimating the wind speeds? So really the sort of the question though is, what are the causal factors that are driving these differences? Can we really parse out the physics of what's going on in these differences in performance between tornadoes and hurricanes? And so this is what Jordan has been working on, is trying to sort of encapsulate all the knowledge that we have, both from a data-driven perspective, all this empirical data we've collected, but also established theory, physics-based modeling, and so on, sort of encapsulate that knowledge in a Bayesian network, where we can sort of look at local, these say nodes that take into account the windstorm type and terrain and wind speed and roof height to sort of get actual local wind pressures, and then relate that to the design and bring in as many of these factors as we can to ultimately inform a damage state. And then again, we can couple the damage state with maybe sheltering behavior. That's a whole stream of factors that we can encapsulate there with time. But then ultimately to, for example, look at the probability of survivability or mortality in different structures given these various inputs that are all defined probabilistically in a Bayesian framework that we can continually update with new data or additional sort of theory and modeling as we move forward. And so lastly here, as I know I'm getting close on time, how can we use something like this? This is another project that recently got through NOAA, where we're now looking at, okay, how could we apply a Bayesian network like this to tornado survivability assessments? So as part of this, again, working with a team of social scientists, they're doing some broad kind of household samples, some baseline public surveys across multiple states, getting hundreds, hopefully thousands of responses from all over on their people's perspectives on risk and vulnerability of their structure and so on. But now we're going to take a sample of those and actually go out and do structural assessments prior to the tornado impacts and try to look for these causal factors, plug those into our Bayesian network, and communicate some level of vulnerability assessment to the occupants, linking their structural vulnerability to the survivability of their home. And so this one is going to be an interesting one. It's going to be a challenge because now we got to take sort of all this stuff that we've, the knowledge that we've encapsulated, but now it becomes sort of real because we're telling a homeowner, we're communicating this knowledge. And again, in a research framework that we'll be very clear on, but trying to communicate it very specifically at the individual home level. Can we do that? And that's going to be the fascinating part of this project as we go forward. So sort of in wrapping up here, coming back to this question, is the solutions to mitigating tornado damage and really improving our resilience. I mean, they've existed for 50 years. Is there any value? And I would emphatically say yes. We still have a long way to go in all of these disciplines: engineering, atmospheric science, social science, and of course, transdisciplinary and interdisciplinary applications of that as well. And of course, I focused here mostly on sort of low-rise buildings and survivability, but there's all sorts of other applications in commercial and power networks and other things that many other groups are working on too. So open invitation. If you want to work on tornado related hazards, there's plenty of room for you to jump in and become involved in this as well. So lastly here, if I may, Richard, is it okay if I take like 2-3 more minutes just for a couple closing thoughts?
Sure, go ahead.
Okay. So lastly, I just wanted to mention very briefly just a couple of things that are kind of closing thoughts, lessons learned for me kind of in my journey to this point. One I would say is don't overlook the fundamentals. As you guys are going through your different classwork, there are so many just cool advancements now in AI and machine learning and chat GPT that it feels like it's so much easier to sort of get knowledge and get code for things and sort of use packages from Python. And I'm not knocking those at all. They're fantastic tools. They're going to accelerate our ability to produce new knowledge in an amazing way. But as you're doing that, don't overlook the fundamentals. As you come out with a PhD, a lot of your value is tied into your knowledge. What is your fundamental knowledge on these subjects that you're taking classes on and so on? And so don't shortcut the learning process and embrace that struggle to understand. Okay, a lot of these things don't come easy. And I give my graduate students examples from my own career all the time. It's okay to struggle. We all struggle. And it's that struggling process that usually sort of drives home that fundamental knowledge. So don't let imposter syndrome sort of take over. It's okay to struggle. And sure, use some chat GPT or so on to sort of help that learning process where it's practical. But sometimes you just got to dig in and try it from this perspective and then come back to it from another perspective and then read that paper for the 4th or 5th time to really get it to sink in. And that's okay. And it will help you in the end. And then third, and something I think that you guys are doing already, just take the initiative. Think about what you want to do as a career and take the initiative about trying to get there now. Or if you're not sure what you want to do, keep your options open, but jump into different opportunities as long as you can see a clear benefit to it. Make a connection, build a network, build your brand. I know you talked at a session on that at the NHERI Summit, which I think is fantastic. Avoid it. A lot of us as engineers are more introverted by nature, and we tend to kind of sit back. But there's so much value in sort of putting yourself out there, trying to make a connection, going up, talk to, you heard a talk from somebody, go up and talk to them afterwards. Don't be afraid of that. It's the natural hazard community is such a wonderful, supportive community. So don't be afraid to take the initiative, make those connections and build that network. And then lastly, find what works for you in terms of work-life balance. This is something that I think a lot of people are, especially in younger career, sort of trying to understand and figure out where things are. Am I going to be working 80 hours a week in order to get a tenure track faculty job or so on? Find what works for you. And really that comes down to, beware survivor bias. I could tell you all about my experience, but I'm a sample size of one. And what worked for me may not work for you. What you hear from somebody else may not work for you. And it maybe if you talk to several people and you see some trends starting to show up, great. But just because someone else did it and worked doesn't necessarily mean that's the only way that you can do it. And then know your life priorities. School, research, job will suck up all of the life that you give it. And so know what your priorities are, what's important to you, what's important to your family or other things, and sort of build your life around those priorities and really focus on efficiency. Think about things as a bounded optimization problem. When I came into my tenure track position, I honestly did not think it was going to work because I had a family with a couple of kids. I made it a commitment of mine. Again, this is just my story, but made it a commitment that, I wasn't going to work on Sundays. That was sort of our time to always be together, to go to church and do things like that. And I didn't know if that was going to be compatible, if I was going to be able to get tenure with something like that. It ended up working out just fine. I worked kind of a set hours, kind of 55 hours a week was my goal. And it worked out just fine. But again, aware of survivor bias, maybe in a different position that wouldn't have worked out for me. I'm not sure. But either way, that was what I felt I could do while maintaining my life priorities and still and to just focus on being as efficient as possible within that time frame. Tension equals equilibrium. We all know that. It's as you're going through kind of life and work-life balance and so on, there's going to be some tension. It's okay. That helps actually hold us in equilibrium, make sure we're sort of focusing on the different roles in our life as needed. And then lastly, no substitute. Success takes hard work. If you want to get somewhere, there's no shortcuts usually to that. Yes, you're probably going to have to work some 55, 60-hour weeks at times to get where you want to go. Maybe it's more than that, depending again on your priorities and what you can do. But there is no substitute for hard work. And it's going to take that to get where you want to go. So with that, just want to say thank you to my amazing graduate students who I've mentioned here, and several of them personally. They're the real brains and the amazing people behind all this research. And then I'll just leave it here with some closing publications and acknowledgments to the National Science Foundation and NOAA. So with that, I'll stop. I apologize, Richard, for going a little bit long.
Oh, that's okay. Thank you, Dr. Roueche. And if you could share these PowerPoint slides with Robin, that would be great as well. Yes, we have some minutes for questions if you have questions for Dr. Roueche. Unmute yourself and or raise your hand, whichever. Comments as well.
Yeah, you can drop something in the chat as well.
Okay. Well, I did have a question, Dr. Roueche, before, just to get everyone going. I don't really understand I'm not into tornadoes. I'm in Oklahoma, so I get a lot of tornadoes, but I don't understand the meteorological side of science. Maybe you have a little bit more understanding of that. Do they not do some kind of tornado wind estimation? Do they not have techniques for that? I would imagine that's kind of the first thing. I mean, the only pseudoscience I have in my head about it is from the Twister movie. So I was like, when I imagine taking data from tornadoes, I'm imagining them throwing little balls in the air and seeing how yeah. So maybe if you can talk a little bit about that.
Yeah, no, that's a great question. And if there's other areas that maybe I'm sort of jumping over or assuming knowledge, feel free to let me know and I can go back and fill in. But yeah, with tornadoes, it's because they impact such small areas that it's really difficult to go out and put instrumentation in front of it to regularly sample. It does happen in things like the Twister, and there is sort of real life Twister of storm chasers that'll go out and they'll fly drones into tornadoes. They'll drop sort of instrumentation in advance of it so the tornado passes over it, and those are super helpful at advancing our knowledge of tornadoes in general. But we rarely get to sample tornadoes like that. And so for the vast majority, the only two reliable options are radar, which we can get a lot from radar, but radar typically is going to be sampling 3,000 plus feet above ground, and the tornado profile is just so different up in those upper levels versus what it is on the ground, which is where it's interacting with our buildings. So radar can be helpful, especially the mobile radar, kind of Doppler on wheels, if you've heard of that at all. Those can be useful. Again, they don't sample everything. And so the vast majority of the time, we estimate wind speeds in tornadoes just based on the damage that it causes. That's sort of the only reliable indicator that we have.
Great, thank you. We do have a question. Yeah, go ahead.
Yeah, do you want me to go ahead and answer that one from Peter?
Sure. You could read it.
Yeah. So Peter asks, could you please share your thoughts on the ethical use of ChatGPT or other large language model AI tools in academic publications? Ooh, that's a good one. I could give my sort of personal thoughts on it, but I know that's very much a developing area, and I see more and more journals now are starting to have kind of official policies on that, which is good. I think my my takeaway from it is, at least right now, and I would love to just discuss it more in general, is as long as it's your own words, I don't see an issue with it. Like using GPT or something like that to sort of analyze your paper and maybe give some recommendations on areas and things like that, would be, I don't think there's anything wrong with that. Where I'd feel a little more, or where I think it sort of crosses the line is if you've got some things and maybe you just tell ChatGPT, hey, rewrite this for me. You just throw some things down and just tell it to rewrite it for you. I feel like we're really blurring the lines there. And then especially if you just give it a prompt of saying, hey, ChatGPT or some other model like that, write a introduction that incorporates, that sort of steps through these, kind of key points. Now I think you've definitely crossed over into, unethical. And so I think there's no one answer for it. I think it's a tool, and it's all in how you use it. But I'm really curious to see where a lot of these publications and sort of how these official policies develop with some of these new tools.
Great, thank you. I guess last question, Shelley. So you have your hand up.
Yeah, thank you. I was just going to ask about the process for building these multidisciplinary teams. I am one of the few social science people here, and how you really put that together and continue to work together on these projects.
Yeah, great question. So these were all pretty organic, and just came from, as I did my own field work and sort of built the reputation on going out in the field and doing these engineering assessments. Maybe I'd share some of those results outside of sort of our engineering conferences. So, for example, I may present at the American Meteorological Society's annual conference, and in doing that, then some social scientists become aware of my work. And then in this case, it was just a meeting after one of the events like that, where it was someone that I had a connection with sort of through another person, and sort of brainstormed this survivability project and or survivor stories project. And then it sort of took off from there. It was just sort of a natural fit, and we found it very mutually beneficial to do this project. And so that was more organic in formation, and we've been doing it now for 4 or 5 years, and we'll try to continue doing work like that with them. And so there have been obviously challenges. We've got an upcoming paper that talks about that. We'll talk about that a little bit more. But social scientists and engineers operate a lot of times at different timescales and different, especially in this post-disaster setting. So there were definitely some challenges early on, but we were all very committed to it and saw the benefit of it. And it's been very rewarding. And then this most recent one was, again, just someone that I was working with here in Alabama, more at in a lot of dissemination kind of resilience workshops across the state. And again, just sort of formed a connection there on some work we could do together. So, I guess in forming those, I would say just don't be afraid to, if you can find a part of your work that's relevant to another discipline, share it. It may be some of their conferences or their, workshop, attend one of them. And you'll sort of build those connections naturally, I think.
Great. Thank you, Dr. Roueche. If you have any more questions, he has provided his email there. We have to move on. We are running out of time to our member presentation. So we do have some research presentations. If you could stop sharing, Roueche. Okay. Let me come back here.
Before we go on, let's just stop and give a round of applause to Dr. Roueche for joining us today. We understand that your time is really precious. If you have to step away, no worries, but we are going to continue our meeting. Thank you so much. It was really interesting, and I especially appreciate the interdisciplinarity that you showed in your presentation. Thank you.
Awesome. Thanks, Robin. Thank you all for having me, and keep doing great work here.